Okay, welcome to the first video for Chapter 4, which is on applications of the derivative. Right now we're going to look at the first section, 4.1, which is on linear approximations and some of their applications. We looked at some of this already graphically using our inspires, but now what I want to do is I want to really do some of the calculations and figure out how to use tangent lines to approximate points on a curve. So, a picture similar to this should be familiar to you. This is kind of what we were playing around with on our calculators to start this section. So if you notice, what essentially we're trying to do is we're trying to come up with a way of approximating a point on a curve. Okay? What we can do is we can find a point somewhere a little bit away from that point on the curve, which we're going to label as A, and we find its tangent line, which we can do. We know how to write tangent lines. We've been doing them for a while now. Okay? To approximate this value delta x units away from A, also known as f of A plus delta x, simply all we do is we walk along the tangent line. So we take the slope of the tangent line, f prime of A, we multiply it by the delta x that we're going across, and that gets us to this point here. Okay? Notice that the distance away, vertically, is really not that far off. And it turns out that as long as you're walking a very short distance along the tangent line, and you can see that here as you walk along this line that I have drawn for you, or rather I got from your book, but this one I'm outlining, it really takes you a while to get drastically far away from the curve. And it turns out that for really small delta x's, we can just use that tangent line to approximate the value of the function at f of A plus delta x. Here's how we do it. So, if f is differentiable at x equals a, and delta x is really small, like I just said, then to get the distance away on the y-axis, the delta f, the difference of the function values, three ways of saying the same thing, we're going to do the derivative at a, which is f prime of a, and we're going to multiply it by that horizontal distance delta x. Okay? Now remember, the actual value, and if you don't believe this second statement, you can go back to the picture from the last slide. The actual difference is going to be f of a plus delta x minus f of a, right? This is the actual delta f here, subtracting these two function values. That's important because very soon we're going to check and see how far off we are from these approximations, so we need to realize how we figure out the exact value. Okay? Remember again, this is an approximation only, and it's only going to work if delta x is small. I can't walk 5 units across the tangent line and really think that I'm going to be that close to the curve anymore. All right, so let's do an example. Let's estimate the difference from 1 over 9.3 to 1 over 9, and we want to see how accurate is our estimate. So right here, this is my delta f, this difference right here. So I've got to ask myself, okay, well, what function am I approximating? And if you notice, the thing that I'm changing is the denominator, so I think the function that we're going to use is 1 over x. Okay? Well, where am I approximating it at? What is my a value? Well, I kind of usually take the smaller of the two values, so in this case I'm approximating at 9. And how far along my tangent line am I expected to walk? I'm going 0.3 away because I want to estimate now 1 over 9.3. All right? So that's what we're going to do. We're going to basically use the slope of the tangent to the curve of 1 over x at x equals 9 to approximate and figure out, well, how much higher up the y-axis do I go to get to 1 over 9.3? So I'm going to use my formula. Delta f is approximately equal to f prime of a times delta x, which will be f prime of 9 times 0.3. Well, I need f prime of 9, so I got to take the derivative of 1 over x. And remember, 1 over x is just x to the minus first. So at this point, this should not be a stretch of your mathematical reasoning to tell me that the derivative is negative 1 over x squared. So at 9, f prime of 9 is going to be negative 1 over 81. So that's what's going to go in this spot in the approximation. So we get negative 0.3 over 81, which we can convert to a decimal, and that is going to be approximately negative 0.0037. Now it wants to know how accurate is my estimate. So I'm going to put up my calculator, and if you notice, I actually have already done 1 over 9.3 minus 1 over 9. Not sure how well you can read that because it's a small calculator, but it turns out that the actual value that we get is going to be negative 0.00358. Okay, so if you want to figure out how far off you are, what the error is, okay, you've probably done this in science class, the error would be the absolute value of the distance between your actual minus your estimate. So in this case, that's going to be the absolute value of negative 0.00358 minus negative 0.0037, which I get 0.00012, or if you like scientific notation, 1.2 times 10 to the minus 4. That's pretty darn close. Okay, that's how far off basically we are from the true versus the actual. In fact, if you want to go back to the picture again, that basically means this gap is only 1.2 times 10 to the minus 4 here. So that's not bad. Let's look at another one. Let's look at one with some trig. So I want to know what's f of 3.02 minus f of 3 for f of x equals tangent of pi x over 3. Okay, so again, this difference is my delta f. So delta f is going to be approximately equal to f prime of a times delta x. All right, well, they already gave me the function. What's my starting point that I have to find the tangent line at? Well, it's going to be right here at 3. So I need to do f prime of 3. So for starters, let's take f prime of x. All right, so I've got a trig function, so I got to go through my list of trigs. The derivative of tangent is going to be secant squared. So I'm going to do secant squared of the inside function, which is pi x over 3. But now notice, this is not just tangent of x. This is tangent of a function. So not only do I have to rewrite the tangent as secant squared, I have to multiply the whole shooting match by the derivative of pi x over 3, which will be just pi over 3. So the derivative at any point is pi over 3 times secant squared of pi x over 3, which means f prime of 3 will be pi over 3 times secant squared of 3 pi over 3, which is really just secant squared of pi. Well, secant to the first power of pi is negative 1. So if we square that, we get that secant squared pi is positive 1. So f prime of 3 is pi over 3. So that's what I'm going to put in as my first piece. The f prime a is going to be pi over 3. And we're going to multiply that by the distance horizontally along the x-axis. And in this case, that's 0.02. So through the magic of using our calculator, if you type that in, you're going to get 0.0209. Okay? Here's another one that I want you to try on your own. So this is the same actual function difference. It's the same delta f. I want to go from f of 3 to f of 3.02, but now I gave you a new function to try. So why don't you pause the video, give it a try. When you're ready to see me work it out, you can pick up where we left off. Okay, so again, f of 3.02 minus f of 3 is my delta f. And the way we find that distance or approximate it is we do f prime of a times delta x. Okay? Well, f of 3.02 is like my a plus delta x. F of 3 is like my f of a. So that means a is going to be 3, and delta x is going to be 0.02. I just need to take my derivative of this function, evaluate it at 3, and I pretty much have the answer, and then I can go to my calculator and get a nice decimal. All right, so to take the derivative of the root x plus 6, remember what this is. This is like saying x plus 6 to the 1/2 power. So we can use our power rule, and we get 1 over 2 root x plus 6, because when you subtract 1 here, you end up with 1/2 x plus 6 to the minus 1/2. Really shouldn't be going through all of the details of these derivatives, but in the case you're still having trouble taking derivatives, that's the work for it. Okay, so now we want to evaluate that derivative at 3. We want to get the slope of that tangent line at 3. So I get 2 times the square root of 3 plus 6, which is going to be 1/6 because that's going to be 9, and we take the root of it to get 3. So that is going to be my f prime of a. My delta x will be 0.02. So it looks like delta f is going to be 0.003333, and the 3's repeat, so you can put bars over that if you'd like. Okay, that's the idea here. Now let's talk about error. So after we estimate and after we approximate, we want to figure out, well, how good a job did we do? So we want to compute error, and we want to compute this thing called percentage error. Again, you've probably seen these words used in science. I remember when I did a lot of labs in high school and science classes, you know, you'd have to measure something, and then you'd compare, well, how does your measurement compare to the actual known value of something? Okay, you do it a lot in chemistry, you do it a lot in physics, I'm sure, when you're collecting data and you're trying to compare that data with what is the theoretical quantity. So to remind you of those formulas, or at least in terms of these types of problems, how we're going to do this. So error is going to be the absolute value of the difference between your estimate and the actual difference. Okay? Now, if you want to figure out the percentage of error, you're just going to take the absolute value of your error, so the thing you get over here, and divide it by the actual difference, and then multiply that by 100, because it's a percentage. So you got to turn the decimal into a percentage. All right, so let's try that here. Let's figure out what delta f is, and then let's figure out how far off we are from our linear approximation. Okay, so they gave me the function, they give me the a, they give me the delta x. This is a little bit easier because you don't have to pull anything out of a difference expression like we've done in the last couple examples. All right, so first step, I need a derivative. So let's take the derivative of 1 over 1 plus x squared. All right, so if you need to, rewrite it. Think of it as the minus first. So this is a chain rule. I've got to take the derivative of the outer power of minus 1 and then multiply that by the derivative of the inside. So f prime of x is going to be negative 1 over the quantity 1 plus x squared squared times the derivative of the 1 plus x squared, which is 2x. So that's going to be negative 2x over the quantity 1 plus x squared to the second power. Okay, that's my derivative. Let's evaluate it now at 3, because that is the a that we're starting from our approximation. So the top becomes negative 6. The bottom is 3 squared is 9 plus 1 is 10. Squared is 100. Okay, so that is going to be f prime of 3. Now, to do my delta f, we simply take that derivative and we multiply it by delta x, which is 0.5. So negative 0.06 times 0.5 is going to be negative 0.03. So that is my estimate difference between basically f of 3 and f of 3.5. Now I want to get my actual difference, okay, because that's how I'm going to get my error. So to calculate my error, I will do f of 3.5 minus f of 3. Now, I'm going to tell you right now, I did all this on my calculator already. So when I did that, I got negative 0.0245. Okay, so now to get the error, we do the absolute value of our estimate, which was negative 0.03, minus our actual value, which is negative 0.0245. And again, through the calculations that I did prior to the video, I get 0.0547. So that's the actual difference away from the curve difference and the linear difference, okay? Going back to that first picture from the first slide, that's that vertical difference between where you are at 3.5 on the tangent line versus where you are at 3.5 on the curve. Now, to calculate the percentage of error, we simply take the absolute value of 0.00547, the error we just calculated, and we divide it by the actual difference, which is negative 0.0245. Remembering that this is a percentage, so we need to multiply that by 100. And we get that we are off by 22%, which is not the greatest of approximation. I guess if we made our delta x a little smaller, our error would probably go down. It's probably because we're a little bit far away. Okay? Now I'd like you to try one. So here's the next one. I made the function a little bit nicer, a polynomial for you to differentiate. But try to go through the mechanics of this as well and see what you can do with it. Okay? Okay, let's take a look at what you did and let's try to compare. So, for starters, we know our function, we know our starting point of 5, and we know in this case we're actually going backwards. Our delta x is negative 0.4, so we're going to the left on our tangent line, which you can do as well. Okay, so, first things first, we need the slope at 5, so we need our derivative. So using the power rule, that's going to be 4x minus 1. And at 5, that means the derivative will be 19, because you do 4 times 5 minus 1. So, to get my change in f, that is going to be approximately equal to f prime of 5 times negative 0.4, because that's going to be our delta x here. So we're doing 19 times negative 0.4, which is approximately equal to negative 7.6 is what I got when I did that. I did 19 times negative 0.4, excuse me. And I got negative 7.6. So now we want to get the actual value so that we can figure out what the percentage error will be. So the real delta f is going to be f of 4.6, because that's going to be f of a plus delta x, minus f of 5. Okay, so if we put in this function and we do f of 4.6 in our calculator, we're going to get that is going to be 37.72, and then f of 5 will be 45. So the actual value is 37.72 minus 45, which is negative 7.28. So to get our error, we're going to do the absolute value of the true difference, negative 7.28, minus the estimated difference of negative 7.6, which will be 0.32. So to get my percentage error, I'm going to do the absolute value of 0.32 over the true of negative 7.28 and multiply that by 100. And that is an error of about 4.4%. Okay, which isn't that bad. So that was a pretty decent approximation. Okay, so one little piece, this idea of linearization. Okay, it's just another way of writing the linear approximation. Sometimes on the AP test, they'll ask you basically, write the equation of a line tangent to a point and use that line to approximate the point maybe 0.2 units over. You know, write the equation of the line tangent at 4 and use it to approximate f of 4.2. Well, that's basically what this is saying. This is just another way of writing point slope for a line. You've got your slope, you've got your point, a and f of a. So that's what you have here. This is actually just another way of writing the original formula that we looked at the beginning of this video. If you do some algebraic manipulations, and it's in your book, if you think of f of x as just f of a plus delta x, because that's what we're doing. We're starting at a, and we're moving delta x away, right? And you plug in a plus delta x for the x's in the equation. You're going to see that basically with some algebra, we get the same formula that we had earlier. Humor me for a second as I go through this. So I have f of a plus f prime of a times, now instead of x minus a, I'm going to do a plus delta x minus a, because I plug that whole thing in. Now look at this set of parentheses. The a's cancel. So I get that f of a plus delta x is approximately equal to f of a plus f of prime of a times delta x. If I bring the f of a over to the left side, I get that f of a plus delta x minus f of a is approximately equal to f prime of a delta x. Oh, and from the very beginning of the video, what do we say this is? The distance from f of a plus delta x to f of a? Well, it's just simply delta f. Remind you of anything? It's the same formula we've been working with. But sometimes you might be asked to use this linearization to do an approximation. I am going to do an example of that. All right, so estimate 16.5 to the 1/4 minus 16 to the 1/4 using linear approximation. Okay, let's do this now, but let's do it using the linearization. So basically, we're going to linearize the function and then plug in 16.5 to figure out where we're going with this value. Okay, so here's what we've got to do. So let me put back up that linear approximation idea, okay? That f of x is going to be approximately equal to f prime of a times the quantity x minus a plus f of a. Okay, so we got to figure out what's f of x and what's a here. Well, f of x is going to be x to the 1/4, because if you notice, what we're doing is we're taking two different numbers and raising them to the 1/4 power. Where are we starting? That's our a value. I think we're starting at 16, and then we're moving 0.5 over. Okay? So let's take the derivative of the function and let's plug it in at 16. So f prime of x is going to be 1/4 x to the negative 3/4, which is 1 over 4 x to the positive 3/4. And at 16, that's going to be 1 over 4 times 16 to the 3/4, which is going to be 1 over 4. Well, it's the fourth root of 16 is 2. 2 cubed is 8. So that's going to be 1 over 32. All right, so this means my linearization of f of x is going to be approximately equal to 1 over 32 times the quantity of x minus 16 plus f of 16, which is 16 to the 1/4 power, and that is going to be 2. So that means f of 16.5 is approximately equal to 1 over 32.5 plus 2. 1/2 of 1 over 32 is going to be 1 over 64 plus 2. So the approximate is going to be 2 and 1/64. Okay, that's f of 16.5. That's the approximation of it. Now we've got to subtract from that the 2, and that's going to be 1 over 64. That's the estimated difference. In other words, I didn't have to actually do all of this step. If you notice, this piece of the formula right here, this is the estimated delta f. Because all we're doing to do the plus 2 is we're just starting at the 2, and we're moving this far over to get to 16.5 on the graph. Okay? Let's try another one. So we're going to estimate tangent of pi over 4 plus 0.02. So again, what is our function that we are linearizing? We are linearizing the function tangent x. What is its derivative? Well, that's secant squared x. Okay. Well, where are we starting? We're starting at pi over 4, because that's our a. Well, that's going to be the secant squared of pi over 4. Secant of pi over 4 is root 2. Squared is just 2. So my linear approximation will look like this. It's going to look like f of a, which is going to be tangent of pi over 4, plus f prime of a, which is 2, times the quantity x minus a. Okay, and the tangent of pi over 4 is 1. 2 times the quantity x minus a. Now, to figure out the tangent of pi over 4 plus 0.02, oops, sorry, it's not x minus a. A is pi over 4. I've got to replace that. I have to replace that in here. So that should not be a anymore, because we know the value of a. A is pi over 4, so it's really 2 times the quantity x minus pi over 4. That'll make sense to you in a minute when we do the evaluation. So to approximate the tangent of pi over 4 plus 0.02, we do f of pi over 4 plus 0.02, which is going to be approximately equal to 1 plus 2 times the quantity pi over 4 plus 0.02 minus pi over 4 Pi over 4's cancel. We get 1 plus 2 times 0.02, which is going to be 1.04. So I know the tangent of pi over 4 is going to be 1, but then when I move it over 0.02, now my tangent becomes 1.04. That is the approximate value of tangent of pi over 4 plus 0.02. Okay? I think this is enough for us to stop. We're going to do a lot more practice with this. Be sure to ask any questions in class tomorrow. The plan is to just really do a lot of linear approximation tomorrow using some of the stuff in this video. Okay? So thank you for watching. I appreciate it, and have a good evening.